In this chapter, we will talk about magnetic forces and fields. Now, we already know that when there is an electric field applied, it can move a charge, and that is what we call electric current. But the moving charge generates its own magnetic field. That's right. Whenever charge moves, it creates its own magnetic field, and so there will be forces acting on the moving charge. This is what we're going to look at in this chapter. But this chapter has so many applications because magnetism is applied in computer devices like magnetic storage, hard disks, is used in toys, doorbells, elevators. Oh, we cannot have a motor without the electromagnetic force. MRI is another application. And then we have levitation, magnetic levitation, where you have those trains that don't touch the rails but keep moving and moving so fast. So all that is in this chapter. But to start our journey, we have to remember that our Earth itself is a magnet. It's a huge magnet. And that we know because if we take a compass and then if the compass is free to rotate, we say that it points in the north-south direction. And it does. But there are two flaws in this thinking. Number one, the compass is not pointing exactly in the geographic north-south direction. No. Because the geographic north-south is a little different from the magnetic north and south. Let's look at this picture. So when you see this diagram, you see that the geographic north pole is right there and the geographic south pole, and this line is actually called the geographic meridian. You have the magnetic north pole and the magnetic south pole. Okay, so that's one thing. So the geographic meridian is not the same as the magnetic meridian. Number two, you may have noticed that the south pole of the compass is pointing to the north pole of the Earth. So we have wrongly named the poles. This should have been called the south pole, magnetic south, and this should have been called the magnetic north, because that's how the compass points. And another thing to remember is that the Earth's magnetic field is not permanent. It flips once a few hundred years, so long intervals. It flips. It's not permanent at all. So with that background information, let's go to the first important section of this chapter, which is when a charged particle moves through a magnetic field, a force acts on it. So you have a charged particle which is moving, you have a magnetic field through which it is moving, and then you have a force that acts on the charged particle that tries to deflect it from its intended path. So in this discussion, you can see there are many vectors. Velocity of the charged particle is a vector, magnetic field is a vector, and the force is another vector. So we're going to talk about what is the direction of this force acting. And that is important. So we have two things to tackle. Number one, we have to look at the direction of the force that acts on the charged particle. And number two, we have to look at the magnitude of the force. So how much force acts on it and in what direction. Before we start off, let me tell you that if the charged particle does not move, however strong the magnetic field is, no force acts on it. Remember that. Second thing, let's say the charged particle is moving and moving very fast. But if it's moving parallel to the magnetic field, again, no force acts on it. So two cases when no force acts on the charged particle. Number one, the charged particle is not moving. And number two, it's moving parallel to the magnetic field. Which again shows that maximum force acts on the charged particle when it moves, you guessed right, perpendicular to the magnetic field. All right, so all that will be clear from the formula that comes up. But here is the the method by which you find the direction. And this is called right hand rule number 1. So you got to have your right hand, not the left. I hope you can distinguish between the two. So you got to have your right hand, and then first you stretch the fingers of the right hand. Let me show it this way. So these point in the direction of the velocity of the particle. So the fingers show the direction of velocity of the particle, and the palm shows the direction of the magnetic field. So the magnetic field is this way. Or sometimes you can, sometimes you say, hey, bend your fingers this way, and that shows the magnetic field. Anyways, so first the fingers show the direction of the velocity of the charged particle, and then the fingers now show the direction of the magnetic field. I think you got it. Velocity of the particle and the palm or the bent fingers show the direction of the magnetic field. In which case, the thumb gives the direction of the force acting on the particle. There is another question that we need to answer, that this only applies if the charged particle is positive. So if it's a positively charged particle moving that way and is moving in a magnetic field which is given by the palm, whatever direction the palm is facing, then the force on the positive particle is acting as given by the thumb. Okay? We'll get to a negative particle later, but that is how we apply the right hand rule number 1 to find the direction of the force. And what is the magnitude of the force? I already specified that 2 cases force does not act. 1, if the charged particle is not moving, and 2, if it's moving parallel to the field. So here is the formula that makes everything clear. Force on the charged particle is given by Q V cross B. It's a cross product. And a cross product always involves sine of the angle between the 2 vectors, which makes it very clear that if these 2 are parallel, then the angle is 0. And sine 0 is 0. No force acts. And also, if the velocity is 0, well, you multiply anything with 0, it becomes 0. So that applies to no magnetic field, no force. No velocity, no force. And no charged particle, of course, no force. Okay, so that's the magnitude of the force acting on the charged particle. All right, what about it's a negative particle? If it's a negative particle, now clear, if it's a negative particle moving towards me, the negative particle is moving towards me, you have to hold the fingers opposite to the direction of motion of the negative particle. Everything else stays the same. So the magnetic field is given by the palm. The negative particle is actually moving towards me, so I have the fingers opposite, and then the force acting on it will be given by the thumb. Which means if actually the negative particle was moving this way, or you're seeing it that way, I had to hold my hand this way. And then if the magnetic field was still the same, are you with me? So the negative particle is moving that way, but I'm holding the fingers opposite. This is the magnetic field given by the palm. The force acting on it is opposite. Simply stated, if a positive and a negative particle are moving through the same magnetic field, the forces acting on it will be opposite to each other. One will be up, the other will be down. I think you got that. I'm sure you understood that. So this formula helps us to define the unit of magnetic field. See, in the International System of Units, magnetic field is not a basic unit because it's always defined in terms of current. You can see that if you rearrange this, all right, let me start this. If you rearrange this, B is F by QV sine theta. So if you give the unit of force as Newton, charge is actually ampere second, velocity is meter per second, sine theta is a number, it has no unit. And then that simplifies to Newton by ampere meter because the seconds cancel out. This is called a Tesla. So Tesla is defined in terms of other units. So Tesla is not a basic unit in the SI, because magnetism is always defined in terms of electricity. Believe it or not, wherever there is an electric current, there's always a magnetic field. We're going to see that. Because whenever a charged particle moves, there will be a magnetic field. So magnetism is studied in relation to electric current. All right, so here is a problem that illustrates the force acting on the electron. So the electron is moving at the velocity given by 7I minus 6J times 10 to the 4 meter per second in a magnetic field B, which is negative 0.8 I plus 0.6 J Tesla. Find the magnitude and direction of the force on the electron. So we know that the force is given by QV cross B. So we'll have to take the cross product. And to take the cross product, we write it or represent it in terms of matrices, which is what I'm doing now. So you have the IJK, and if you look at it carefully, I is 7 times 10 to the 4, and J is negative 6 times 10 to the 4. That's for velocity, and then for B, it's I is negative 0.80 and J is 0.60. So that's what I've written there. And both of these do not have the K vector. So we have that. And then I presume that you know how to take the cross product. If you don't, here is a quick review. So to find the coefficient of I, we would just multiply J times K minus this times this. Okay, so you go this way, multiply these two, and this way. In this case, both of those will be 0. And then to find the coefficient of J, you multiply that for I and K. But remember, you got to put negative J and do that. So then you would multiply this with this and this with this. Oh, that would both also be 0. So finally, you have to find the coefficient of K, you would multiply this with this minus of this with this, which is going to give us two numbers. And we got to be really careful about the sign. When you do this carefully. So here it is. So you get the charge of the electron written again, and then inside 7 times 0.60, you see that? 0.60 minus of minus 6 times 10 to the 4 times negative 0.80 K. And then you do that math, find how much that is. So that's going to give what, 4.2? Yeah, and then there is 10 to the 4. Okay, hold on. Why is that? Because what I did is, I just took the difference between the two to make it easy. Okay, so the difference is going to be 0.6 times 10 to the 4, because you have 7 here and then you have 6. Is that making sense? So you get negative 0.6 times 10 to the 4 K, which finally gives you, when you multiply, it gives you 9.6 times 10 to the negative 16 Newton along the K axis, which is the Z axis. So here's another question. This time, the force is given. The electron is experiencing a force of that much. It has the I and the J components when passing through a magnetic field which only is along the K axis. So, and now you've got to find the electron's velocity. So you have to rearrange the formula. Once again, we know F is QV cross B. So represent that in the matrix format as before. So the force is itself going to have 3 components, Fxi, Fyjy. It will not have the K component in this case. Remember, whatever is parallel, there won't be a component. So here the force will only have I and J components because the magnetic field is along K. And then to find the velocity, we just put it as Vx, Vy, Vz because we do not know what they are. And then you also have 00BC. Let me just complete that so you see what I'm writing. So you have 00BC here because we know the magnetic field is only the K. I should have written I, J, K here. That's understood. And then when you do this part like before, you're going to get Vy Bc, which is there. See that? For the coefficient of I. And for J, we are going to have another component that's coming up, which is minus Bx Bc. That's for J. So those are the only two. Everything else becomes 0, and you need not write that. So take a look at it carefully and you'll understand why and how I've written this. Of course, I've multiplied both with negative E, which is the charge of the electron. And then that leads us to, the coefficients of I on both sides must be equal. So the coefficient of I here is all this, and the coefficient here is Fx. So we put them equal to each other. So Fx becomes equal to all of this. Okay? Then rearrange that to make Vy the subject, which gets us minus Fx by EBz. And then that is the force that's given, 3.8 times 10 to the negative 13, divided by the charge of the electron, and then Bz, which is 0.85. Calculation gives negative 2.8 times 10 to the 6 meter per second. Do the same for the y. So the coefficient of y here, which is j, is all this. And then on that other left side, it's fy. So put fy is equal to that. Rearrange and make Vx the subject. Substitute the values given, charge of the electron and this, and you get that formula. So now we got the components of the velocity along the x and along the y, and put them together, and that is the velocity of the... Now I just want to give you some important properties of magnetic field lines. As you can see here, the field lines due to a magnet start from the north, go to the south, and continue inside from south to north. So magnetic field lines are closed as compared to electric field lines, which are open. So they start from the north, do not just finish on the south, just loops back to the north. So that's one thing. The second thing is, if you look at lines that are really close, then you know that it's a stronger magnetic field there. So that's why the strength of the field is proportional to the density of lines. So if the lines are closer, then the field is stronger. And then if there are no lines passing through a certain point, as in this case, where you have the two north poles, that means there is no magnetic field there, obviously. It's actually called a null point or a neutral point. Okay? And then another thing is that, all right, let's go magnetic field lines. You will never see magnetic field lines cross each other. No, they cannot intersect, because the tangent drawn to a magnetic field line, a tangent at any point. So if you take a point here and draw a tangent to this curve, that will give you the direction of the magnetic field at that point. So important, the tangent drawn to a magnetic field line at any point gives the direction of the field. So if two lines actually cross, then what we're going to have is, we'll be able to draw two tangents, one to each, which is impossible. Because at one point, magnetic field cannot be along two directions. I hope that makes sense. So that's why magnetic field lines can never intersect. And magnetic field lines are closed, I told you that. It is actually from the north to the south outside, but inside it is from the south to the north. Also remember that. So be careful about that. So that's just a snapshot of the properties of magnetic field lines. Okay. Yep. I told you that the field direction is the tangent drawn to that line, and I've actually showed it to you now. See, that's the direction at that point. And at this point, this is the direction. It's along the tangent drawn. Moving on, field lines do not intersect. I've also told you that. Oh, this is a very important situation. So in this case, let's imagine that the magnetic field is wide enough. That means it's in quite a big space, as you can see by the yellow region. And if you look at these crosses here, That's like you're seeing the back part of an arrow, right? Back part of an arrow, which means that the magnetic field is perpendicular to the screen and into it. So the magnetic field is perpendicular to the screen and into the screen. That's what the cross shows. On the other hand, if you see dots, then you would be seeing the tip of the arrow, which means the magnetic field is now out of the screen perpendicular to it, okay? So it could be in, it's a cross. If it's out, it's a tip. And let's imagine that there is a charged particle, a negatively charged particle that enters this magnetic field. So as soon as the charged particle enters the magnetic field, by using the right-hand rule, we can show that the force acting on the particle is downwards. So when the force begins to act on the particle is going to swing down, right? It wanted to go straight, but there is a force acting down, so it'll bend. When it bends, the force also bends, because the force is always at right angles to the motion. So that keeps on happening, and finally the charged particle is compelled to move in a circular path if the magnetic field is spread out in a wide area. Otherwise, if the magnetic field is only in a shorter space, or smaller space rather, it would just curve and go away. But if it's in a wider area, it will make a circular path, okay? When anything moves in a circular path, there must be the centripetal force acting on it. The centripetal force is given by mass times velocity squared by radius. Mass times velocity squared by radius. And in this case, the centripetal force is nothing but the magnetic force, which we know is QVB sine theta. That's why I've written that formula down. But theta is 90 degrees. What is theta? Theta is the angle between the velocity. Remember, the electron was coming in the plane of the screen, and the magnetic field was perpendicular to the plane. So the angle between velocity and magnetic field is 90. Sine 90 is 1. That's why that's missing. So now we have QVB is mv squared by r. If you rearrange that, you get a formula for the radius. If you look at the formula for the radius, you understand that the higher the velocity, the bigger the radius. But the stronger the magnetic field, the smaller the radius. So if the magnetic field is stronger, it'll be compelled to make a smaller circle. Okay? Because there's a bigger force acting on it. So look at that. It also depends on the mass of the charged particle and the charge. Okay? So that's for the radius. Now from here we can find the time period taken. What is time period? It's the time taken for one rotation or one revolution. Time is what? Distance by velocity. And distance is going to be the circumference, which is 2 pi r divided by the velocity. And if you rearrange this formula, you get velocity as, you can see that you can substitute for velocity as qbr by m. Well, I did it in 2 steps because I think what I did is I substituted for radius here. So you see the radius is mv by qb either way. And then the velocity will cancel out and you would get 2 pi m by qb. Okay. Wow. That means the time period is independent of the velocity. Oh, whether the charged particle is coming in slow or fast, it'll take the same time period. Why? Because if it's coming in fast, remember the radius is small, so it'll go that way, in a smaller radius. But if it's coming in slowly, then it'll go with a smaller, slowly, the smaller radius. So it's a smaller radius. So one case it's a bigger radius with a faster speed. Second case it's a smaller radius with a slower speed, which kind of makes sense. They will be taking the same time. So that's for time period. But then we also need to think about, what if the charged particle is not entering exactly perpendicular to the magnetic field? Okay, what if it's coming at an angle? If it's coming at an angle to the magnetic field, then we'll have to break the velocity into its components. So now the velocity will have a component which is perpendicular to the magnetic field and a component which is parallel to the magnetic field. Correct? Does that make sense? And the component that is parallel to the magnetic field creates no force. Remember, when a charged particle moves parallel, there's no force acting on it. So that velocity is unaffected. But the perpendicular component will make it go around in a circular path. So now you have to have two motions combined. Circular motion combined with straight line motion. That will give it a helical path. So helical motion, as you can see in the diagram, the perpendicular, here it is. The perpendicular component makes it go around in a circular path. The parallel component just makes it go forward. So a combination gives you a helix. And those are the components, V sine theta and V cosine theta. And pitch of the helix is just this distance, pitch of the helix. To find the pitch of the helix, multiply the parallel component with the time taken, because you know that if it starts from here, it takes the time period to come back there, right? And in that time, it's moved forward. So since we are trying to find out that, we need the time period to be multiplied with the parallel component, because displacement is velocity multiplied by time. So when you do that and substitute, you're going to get, all right, time period is 2 pi m by qb. We already know that. We need to multiply that with v cosine theta, and you can solve the problems. I've not shown that there, but you can do problems using those formulas. That's in the case of a particle that's entering at an angle. So here's the problem. An electron enters a uniform magnetic field 0.28 Tesla at a 45-degree angle to B. I picked 45 because when you take sine 45 and cosine 45, you get the same number. You've got to find the radius and pitch of the electron's helical path, assuming its speed is 3 times 10 to the 6 meter per second. Okay, so the same formulas, I just copied that diagram there. And the radius is given by mass times the perpendicular component of the velocity divided by qb. And when you take the mass of the electron, the perpendicular component is what? 3 times 10 to the 6 sine 45 divided by the charge of the electron times the magnetic field, which is 0.28. When you do those calculations, you get 4.3 times 10 to the negative 5 meter. And then we find the time period using 2 pi m by qb. So 2 pi times m by qb will give you that. Once you get that, you multiply it with the parallel. Okay, that should have been the parallel component, which is velocity cosine 45 times 2 pi mb by qb. Okay, I'm writing the whole thing there. Okay, so that's where you would get that. So what happened to that? Okay, there it is. So Q and B. So that gives 2.7 times 10 to the negative 4 meter. Obviously, that's a small distance. So we're talking about minute distances, okay, on that. So that's how you work out that problem. The next topic is where you have a current carrying conductor situated in a magnetic field. So instead of a charged particle, you have a current flowing through a conductor, and the conductor is placed in a magnetic field. Essentially, it is the same idea, because a current is nothing but flow of charges. So all we got to do is find the total charge that is flowing through the conductor. So that's why I've written this formula. You know that current is NEA times the drift velocity. And if you look at these terms, you understand that N times E times A gives you the total charge, because N is the number of electrons in 1 meter cube and A is the area. But if you multiply that with the length, then you would get the total number of electrons. So look at this, NA dl. I've included the length of the conductor now, times E times Vd. And those that I've underlined, if you multiply those, You see, NAVDE actually gives you I. See, NAVDE is I. And then what you have is L cross B. Because this is the small force acting on a small length. And if you want the total force acting on the whole length, the dl is going to become L. So that's the only difference. So that's the formula for force acting on a current carrying conductor situated in a magnetic field. What's the formula? The force is I L cross B. It looks like the previous one, but there's a difference. I L cross B. And to illustrate that, here is a question. Suppose a straight 1 millimeter diameter copper wire could float horizontally in air. Wow, is that really going to happen? We'll find out. A copper wire is floating horizontally in air because of the force due to the Earth's magnetic field, B. That means the weight of the wire is being balanced by the force due to the Earth's magnetic field. They must be equal and opposite. And they're saying which is horizontal. What? The magnetic field of the Earth is horizontal, perpendicular to the wire, and of magnitude 5 times 10 to the negative 5 Tesla. What current would the wire carry? And then, does the answer seem feasible? From the outset, I think it's not feasible. Have you ever seen a copper wire float just like that in the Earth's magnetic field? We'll find out why. But the idea is the weight. So that's the wire. The forces acting should be equal and opposite. The forces are mg is the weight, and ILB sine theta. Theta is 90. So that's why ILB is equal to mg. And you just need to make I the subject. But to find the mass, you need to multiply volume with the density. That's what's coming up here. Mass is volume. Isn't that volume? Pi r squared times the length is the volume times the density. So that's the mass, the whole thing. And then if you substitute all this, of course, you will be given the density, which is 8.9 times 10 to the 3, then pi r, which is half of the diameter. Be careful with that. And if you don't remember it there, you can just divide it by 4 because you're squaring it, remember. See if I do that. So 1 times, did I? Okay, let's find out. Times 980. That is diameter, and I used it as the radius. Oh, now I did it. Okay, I did it. I didn't catch it initially. You saw that. But then I divided by 4, and then I calculated, and the current is what? 1400 ampere. Wow, that's a huge current. That current is so large that it would instantaneously melt the wire. So that's not practically feasible. That's all I'm saying. That's just to show you how to work out a problem. So we extend this idea of a force acting on a current carrying conductor kept in a magnetic field to that of the force or the torque acting on a rectangular loop situated in a magnetic field. So the loop is placed in such a way that it's capable of rotation. So this is actually the principle of a generator. Or rather, this is the principle of a motor. Motor and generator, basically, they have the same construction. A little difference in the working. Let's get that now. So this is interesting. So if you have this rectangular loop situated in the magnetic field. Remember, the magnetic field is from north to south. And you see this is DC, so current is coming in, flowing through that, the loop, and then flowing out through this. And you have a brush split ring. That's what this is called. It's a brush that's touching against or rubbing against a ring that's split into two. It's because you can't have permanent connections there. It'll get tangled up. So that's what it's called. It's actually called a split ring commutator. We'll get into that later. But anyways, when the current begins to flow, there will be a force acting on this side downwards and on this side upwards. Why? Because on the left side, the current is flowing one way. On the right side, it's flowing in the opposite way. You see? Since it's flowing in opposite direction, the current, the forces will be opposite, but they will be equal. So now you have an equal and opposite force acting on the loop. And what about on these sides? No force. Why? Because the current is parallel to the magnetic field. Because the magnetic field is from north to south, currents are parallel or anti-parallel, no force acts. So there's only force on the two longer sides. One force up, the other down. That creates a torque, which tends to rotate this. And to find torque, we just have to find the force and multiply it with the perpendicular distance between them. And you know the perpendicular distance between them is the width of the coil, isn't it? Yeah, the width of the coil. So the force we know is ILB sine theta, and torque is R cross F. That's why I said perpendicular distance, which makes it B ILB sine theta. You see that I included B, which is the breadth or the width of the coil or the loop. Everything else is the same. But what is the product of width and length? Isn't that area? Yes, it is. So that becomes IA. So A is the area of the loop. And that is for one turn, right? Yeah. But before we go further, this can be written as a cross product. This can actually be written as IAN, where N is a unit vector, which is perpendicular. That's we're trying to define what's called the magnetic moment. Magnetic moment, mu, is the magnetic moment. What is magnetic moment of a loop or of a coil? It's simply the product of current and area. Important. What would the unit be? It would be ampere meter square. Yeah, ampere meter square. So the product of current flowing through a loop and its area is called the magnetic moment, represented by mu. And it has a direction which is perpendicular to the plane of the loop. So if that's the plane of the loop, the magnetic moment is perpendicular to it, okay? And then we can rewrite this for n turns. If there are n turns, you just multiply this with caps n, because this is in the case of a single loop, isn't it? So if there are n turns multiplied with n, and then you would get mu would be redefined as NIAN, and so torque would then become mu cross B. See how that worked out? So because mu is NIA, so you have the NIA here, and then what do you have? Then you have B sine theta, which is mu cross B. Got it? So the torque is simply the magnetic moment with the cross product, the magnetic field. Okay. So I'm trying to write that now. NIAB sine theta is what you get from there. Okay. And here is a problem illustrating that. It says, calculate the magnetic field strength needed on a 200 turns square loop, 20 centimeters on a side, to create a maximum torque of 300 Newton meter if the loop is carrying 25 amperes. So what do you have? You have the number of turns. You have the side, it's a square, so 20 centimeters. You have the maximum torque, and you have the current. We are asked to find the magnetic field. It's simple case of substitution, because we know that torque is NIAB sine theta. Okay, so for maximum, it says maximum torque. It gives you the maximum torque. That means theta is 90, because that's when sine 90 becomes maximum, which is 1. So we have maximum torque is NIAB, rearrange. You get B is tau max by NIA. Substitute. The maximum torque is 300. Number of turns, 200. Current is 25. Area, be careful on that. It's 20 centimeters. So it'll be like 400 centimeters square, which becomes 0.4 meters square. Be careful. And then when you calculate, you get 0.15 Tesla. So that's how you work that problem out. Now let's focus our attention on the applications of what we have studied so far. We're just going to have a few applications. The first one is what's called a mass spectrometer. A mass spectrometer is the device which enables us to find the isotopes of an element. You know what isotopes are? Same atomic number, different mass number. And the spectroscopes or the spectrometers use this idea. So here is the construction. First, you have a source that produces charged particles, and then they come in through what is called a collimator. Anyway, so you get a fine pencil of charged particles. They enter a space. Look at the space. In this space, you have an electric field and a magnetic field. But these two fields are perpendicular to each other. So the crosses represent a magnetic field that is perpendicular to the screen and into it. But the electric field is in the plane of the screen from right to left. So one is into the screen, the other is from right to left. So the two fields are perpendicular. Actually, these are called crossed fields. So the electric and magnetic fields are perpendicular. What's going to happen is when the charged particle enters the space, both the electric field and the magnetic field will exert a force on it. But the forces on the particle will be opposite. So the magnetic field would be trying to move it to the left and the electric field trying to move it to the right. And if we can adjust the values of the electric and magnetic field, we could make the two forces equal. So what happens is the two forces are not only opposite, but they also become equal. What does that do? Oh, that means there is no net force acting on the charged particle, and such charged particles will continue their journey. This method of filtering charged particles is called a velocity selector. Because when I write the formula, you'll understand it's only particles that have a certain velocity that will have the equal forces acting on it. It's called a velocity selector. And after you filter those particles, you're sure that all of them have the same velocity. Now they are allowed to enter another magnetic field. You see, in a broader area, this magnetic field is also perpendicular to the screen. And when those particles, all having the same velocity, enter that space, they are compelled to go in a semicircular path, and then they go and they are detected by a particle detector. And the radius that they take will depend on the velocity and the mass. And so from where they are detected, like the radius, from the measurement of the radius, we'll be able to calculate the mass of that particle. So if all of these particles are coming from one particular element, and you get like two different radii, then you know, wow, this element has atoms with two different masses. And we can even calculate the mass of those. That's how we are able to find the isotopes of an element. So let's put that math. So I already told you about the velocity selector. That's when the velocities become equal. The forces become equal. What are the forces? The force due to electric field is QE, and the force due to a magnetic field is QVB. They're equal, so the Q's cancel out and velocity is E by B. Oh, it's only the particles that have that velocity that will go through. And the next, we know that the radius, when it enters the second magnetic field, is represented by B naught, see that? Is given by MV by QB naught. From where we can make Q by M the subject. Q divided by M. That's charge divided by mass. It's called the specific charge. Specific charge, another technical term, and that specific charge is given by this formula. Simple math from there. And then we substitute for velocity. What is that? Isn't that E by B? So finally you end up with this. So Q by M depends on these quantities. And the only variable there is the radius. I hope you understand. These three are constants. So the only variable is radius. That means if you have two different specific charges, you're going to have two different radii. If you have three, then you have three different specific charges. So that's how you find isotopes. Here is a problem that illustrates this. says, what's the velocity of a beam of electrons that goes undeflected? That's the word, that goes undeflected when passing through perpendicular electric and magnetic fields of magnitude, both given. One is electric field, volt per meter, and the other is in Tesla, so that's the magnetic field. And then you're asked to find the radius of the electron orbit if the electric field is turned off. We'll come to that later, but first of all, how do you find the velocity? It's just simply E by B. I'm just writing all of it again, but that's how we got it. E by B. Simply divide the electric field strength divided by the magnetic field strength. And you would get 1.173 times 10 to the 6 meter per second. It's approximately 1.2 times 10 to the 6 meter per second. That's fast. Yes, it is. And then second part, what's the radius of the electron orbit if the electric field is turned off? So now you only have the magnetic field, and we know the formula for radius. We've written that so many times. I'm trying to write it again, but we've done that many times, and finally you end up with radius is mv by qb, and mass of the electron, in terms of velocity that we got just now. We don't use the rounded off value, we use the actual value there. Charge of the electron times the strength of the magnetic field, which is 8.8. Wait. Oh, sorry. 7.5 times 10 to the negative 3 Tesla. I was reading the electric field. And then you get the radius, 8.9 times 10 to the negative 4 meter. Yet another application of this is what's called the cyclotron. The cyclotron is a particle accelerator. That means it can take charged particles and accelerate them to very high velocities so that they can then be used to produce maybe nuclear fission, where the fast-moving charged particle now hits a nucleus and divides it into so many parts. So anyway, this is a particle accelerator. It's called a cyclotron. Here is the construction. It's actually, we'll look at this side. You see two Ds. They're actually called Ds because they have the shape of the English letter D. This one especially, and the other one is backwards. So these are flat on top, flat below. It's hollow inside, hollow. And at the center of these Ds, you have a source that produces particles, charged particles at the center. And so you see that there, right there. And an alternating field is given to the Ds. What do you mean by alternating field? That means they make the Ds positive and negative. So at one time D1 would be positive, next half a cycle D2 would be positive. And so that keeps repeating. That's why it's called alternating potential. Okay? And right when this D1, let's imagine this is a positive ion, just to explain, positive ion, and when it just comes out, if D1 is negative, being a positive ion, it'll be accelerated towards it. So that's why you see that coming in. And then also, I forgot to tell you this, that right outside you have the north and the south pole, you see. So there's also a magnetic field from the north to the south. So you not only have an electric field, you also have a magnetic field which is perpendicular to the electric field. And because of the magnetic field, the particle is compelled to move in a circular path, or in this case, a semicircular path. Negative. D2 becomes negative. So now the particle is accelerated towards D2. And also remember, once the particle enters the D, there is no electric field inside. So the electric field is only in the gap. Don't you remember that there is no electric field inside a charged conductor? So the acceleration happens only in that space, just in that space. But this time it's moving faster. So it'll go over a bigger radius, see that? But the timing is such that, remember, the time does not depend on the velocity. So once again, when it reaches the gap, now D1 has become negative. So now it's moving faster. So the radius is even bigger. So this process is repeated many times. And each time, the particle is moving faster and faster. And finally, it comes out with a huge velocity. So that is the idea of a cyclotron. So here are the formulas. The radius of the path at any time is mv by qb. Time period is 2 pi m by qb. And if you take the maximum velocity, so I'm just rearranging this, to make velocity the subject. Wouldn't that give us qbr by m? Yeah. And if you're looking for maximum velocity, because these three terms are constant, that means radius must become maximum. So that's why when the radius becomes bigger, the velocity becomes bigger. Once you get the maximum velocity, you can figure out the maximum kinetic energy. Kinetic energy is 1/2 mass times velocity squared. So 1/2 m Vmax squared. So when you substitute the value of Vmax, you get all this. You have to square each term, so you get that. So that's the calculation of maximum kinetic energy. So that's the principle of working of a cyclotron. Okay, frequency, all right. Frequency is 1 by time period, is the reciprocal of time period. So that's actually called the cyclotron frequency. So be careful. It's flipped here because frequency is 1 by time period. Okay, so there is a problem that I've done here. The radius of a cyclotron is given. Magnetic field strength is given. What will be the maximum Ke? Now, to save time, maximum Ke is given by this formula, isn't it? Just a matter of substitution. So Q squared, B squared, R squared by 2m is a charge of the particle. Oh, these are protons, so that's the charge. Then you have B, strength of the field, radius, 2 times the mass of the proton. So that's the mass of the proton. That gives you 6.898 times 10 to the negative 13 joules. You will be like, well, that's not much. Well, in the microscopic world, that's a lot of energy. Remember, these particles have such a tiny mass, and so compared to that, their energy is really, really big. That's why you can use this as a projectile to produce maybe nuclear fission, as I mentioned before. Oh, and to finish this discussion and this chapter, I just want to mention that usually kinetic energy is represented in terms of electron volts. So there you will see how big the energy is. How do you change it into electron volts? You divide joules by 1.6 times 10 to the negative 19. But I want to represent it as mega electron volts. So once again, you divide with 10 to the 6. Mega is like million, 10 to the 6. So then you get 4.3 mega electron volts. That lets you know that that's a lot of energy. That's like the energy gained by an electron when accelerated through 4.3 million volts. Imagine. So that's a lot of energy. That's the only purpose why I changed it into mega electron volts. So that is your chapter. Quite an important chapter where we looked at the forces acting on a charged particle, on a current carrying conductor, and then on a loop. All right, so and then we looked at 2 applications. One is the spectrometer and the other is the what? The cyclotron. So hopefully you understood this chapter well. By compulsion, I have to move fast, but I know you can always pause, listen to it again. That's one reason why I'm moving fast. Listen to it carefully, understand the concepts, and do well on the exam. See you on the next video. Thank you. Cut.